Hi, so in this video we are going to see an example of the 0-1 knapsack problem. So let's get started. The typical situation is like this. We have the so-called knapsack table with the weights and the items. We have n equals 3 items and we have a maximum capacity of the knapsack m equal to 5 kilograms. So we can put up to 5 kilograms into this knapsack. We cannot put 6, 7 or 8 kilograms because we cannot exceed the capacity of the knapsack when putting items in it. So the item 1 has a weight W1 4 kilograms and it has a value V1 $10. The second item has a weight 2 kilograms and it worth $4. The third item has a weight 3 kilograms and it costs $7. So the knapsack table, the column represents the weights 0 to the maximum capacity of the knapsack, and it is an integer programming problem, so we cannot have 2.5 kilograms. As I said earlier, it is not the first problem, the dividend knapsack problem. We saw that the greedy algorithm is feasible. We can use the greedy algorithm, but in this situation we cannot use the greedy algorithm because we have to choose whether to take an item or not, and that's why it is an integer problem. We have integer weights and integer items. So the columns represents the weights and the rows represents the items. And because we have subproblems, we have a subproblems when there is no items. It's very easy because we are going to fill the table with zeros, because if there is no items, of course we cannot put anything into the knapsack. And then we have only a single item with index 1, and we solve the subproblem and assume we have only one item. Then we assume that we have the first two items, and we are going to rely on heavily on the previous row of the knapsack table, and this is why we call it dynamic programming, because we are going to rely on the previous row's information. So we keep updating rows by rows, and we come to the conclusion that we can get the feasible solution with the help of dynamic programming. Of course, we are going to get the situation when we have to consider all items, item 1, item 2, item 3. So let's get started. And of course, it's worth considering, mentioning that it is the magic formula in yellow, that AIW equals to the math.max AI minus 1W. This is a situation when we do not take the item with index I, and of course there's a situation when we take it, so we have to, there's a VI representing the value plus AI minus 1, V minus VI. So in this situation we take the item with the ith index, so we get the value with VI, and we have to subtract the VI weight from the knapsack's weight. So let's get started. We have to update the table, so if we have no items, of course we have to fill it with zeros. And of course we have, if there is zero weight we can carry, of course we cannot take any items because all the items have greater weight than 0. So the first row and with index 0 and the first column with index 0 is going to be null. So let's get started. If we have only one item, the first item that has 4 kilograms and it has a value $10, of course we cannot put into the knapsack if it can carry only 1 kilograms. So the header of the columns represent how many kilograms the knapsack can take, And in this situation, 1 kilograms and 4 kilograms is greater than 1, so we put a 0 in this position. If we jump to the third row with index 2, it represents that the weight is the capacity of the knapsack can carry 2 kilograms, and 4 is greater than 2, so it is 0. 3 kilograms is less than 4, so it's 0. And we come to 4, we see that the first item weight is 4 kilograms, so if the capacity of the knapsack would be 4 kilograms, then we can take the first item, and for the first item we get $10, and that's why we put 10 in this location. The next one, it is the knapsack in this situation can carry 5 kilograms, but we have only one item, and this item has only 4 kilograms, so we can put the 4 kilograms in a 5 kilograms capacity knapsack, and we get the value, which is $10. If we have two items, we can rely on the formula, the magic formula, because in this situation and from this situation, these kind of calculations are not so straightforward, so we can use our equation, and in this situation our equations tell us that the A with row index 2 and column index 1, we have to consider the maximum of two integers, the A11, which is, we can look up in the table, the row index 1 and column index 1, there's a 0. And the second item is $4, because that's the value of the second item, plus the A1, 1 minus 1, and because the index 1 minus 2 is equals to minus 1, and our table, it starts at 0, it is an invalid index, so we consider it 0. So we have to decide the maximum between 0 and 0, which is 0. So we put a 0 to the A row index 2, column index 2. We jump to the next column, and it's going to be 4. Why? Because A22 is equal to the mass that max with index A, 1 and 2, which is, we can look up in the table. It is the row index 1 and column index 2, there's a 0. And the second integer will be $4 plus A, 1, 2 minus 2. We can look it up in the table. The row index 1 and the column index 0, there's a 0, so $4 plus 0 is equals to 4. We have to decide between 0 and 4, so it is the 4, because 4 is greater than 0, so we put a 4 there. Jump to the next column. It is a 4. Why? Because we have to calculate our magic equations, or magic formula. A23 is equal to the mass that max. We can look up the table, the A with row index 1 and column index 3. It is, of course, 0, and we calculate the $4. Why $4? Because we're considering the item with the second index, so the second item, and the second item has a value of $4. So $4 plus the value in the lookup table with row index 1, column index 3 minus 1. If we look it up, we come to the conclusion that it is 0, so $4 plus 0 is equals to 4. We have to decide whether 0 is greater or 4. We come to the conclusion easily that 4 is the integer we are looking for, so we put it into the right place. Okay, the next one is 10. Why? Of course, again, we just have to calculate our formula. So A with row index 2 and column index 4 is equal to the mass that max A14, which is 10, and we have to calculate the other situation when we take the item. So it's very important that the first integer in the mass that max equation represents that we don't take the item with index I. In this situation, index 2, so we cannot take the item 2. In the equation, the $4 plus A 1 and 4 minus 2 represents the situation when we take the item with the index 2, so we take the second item, and we have to calculate that is it a good option if we take it with us or not. So this is why we have to calculate on each iteration. And A with row index 1 and column index 2, it is a 0, I think. Yeah, it's a 0, so 4 plus 0 is 4. So we have to decide which is the greater, 10 or 4, and it is 10. So we put 10 in this location. The next one is also 10 because we have to calculate the in the lookup tables, we just have to look up the integers, row index 1, column index 5, it is 10, and we have to calculate the row index 1 and column index 3, which is 0. So, $0, $4 plus 0 is 4, so we have to choose between 10 and 4. We have to take the maximum of these two numbers, and we come to the conclusion easily that it is 10. So, we keep updating our table like this, and we do it for the last element, and of course it is for the row index 3 and column index 1, it is 0. As I said earlier, if we have the situation like in here, that we want to calculate the A with row index 2 and column index 1 minus 3, we wanted to calculate something where the column index is less than 0. In this situation, we consider the whole stuff to 0, no matter that there's a $7 in the beginning. So it is 0, and A21 is also 0, so it's going to be 0. The next item is going to be 4, because we calculate the mass.max. The second row index and second column index, there's a 4, and because the index is less than 0 on the second expression, so we take the 4 because it's greater than 0. Then it's 7. Why? Because in the lookup table, the integer with row index 2 and column index 3, there's a 4, and integer with row index 2 and column index 0, there's a 0, but $7 plus 0 is equal to $7, and 7 is greater than 4, so it's going to be a 7. Then it's going to be the 10, because we have to look it in the tables, and we come to the conclusion that we have to decide between 10 and 7, and 10 is greater, so it's going to be 10. And in the last row index and last column index, it's going to be 11, because the row index 2 and column index 5, there's 10, and we have to look up the knapsack table with the row index 2 and column index 2. It's going to be a 4, so $7 plus $4 is going to be 11, and because 11 is greater than 10, it is going to be the winner.
So we have calculated and made a solution. The value in the last row and the last column is the solution we are looking for. So we can make $11 from the items we have taken. But the good question is, what are these items? What are the actual items to pick? And it's very important that we start at the last row and last column with the 11 value we have specified, and I colored it red. And we have to compare it with the value above it. And we come to the conclusion that it's 10. 10 is not equal to 11, which means that we have to take item 3. If these two numbers were matching, it means that we do not have to take item 3. But because 10 is not equal to 11, we have to take it. So we come to the conclusion that we have to take item 3 with weight 3 and value $7. Then we have to consider the item 2, we have to go forward, upward, because we have already taken the third item, we have considered the second one. And because we have taken the item 3, and the weight of the item 3 is equal to 3 kilograms, we have to take 3 steps to the left as the value of the weight. So if we go, we come to the conclusion that we end up at 4. And because 4 is, we have to compare again with the value above it, which is 0. 0 is not equal to 4, which means that we have to take item 2 as well. And because item 2 has a weight 2 kilograms, we do not have any more weight left, which means that we have solved our problem. We have to include item 3 and item 2 in our knapsack, and it is quite self-consistent. If we take a look at item 2 and item 3, $4 plus $7 is equal to $11, and that's what the value we are going to make. And the capacity is 2 kilograms plus 3 kilograms, which is 5 kilograms, the maximum capacity of a knapsack. So it can be a feasible solution. So this is how we solve knapsack problem. Thanks for watching.